Okay, welcome back. This is the October 2024 Unit 5 Physics exam for Edexcel IAL. I went through Section A, the multiple choice, in Part 1, and here's Part 2. I'm going to go through two questions because although they're short, in the second question there's quite a lot of maths. Okay, so don't forget to like, share and subscribe, as each video is about 10 to 20 minutes long, and I have a multiple series of videos that I'm going to put up for each paper. So just make sure that you hit the notification. I think that's the bell you got to hit after you subscribe, and it will then let you know when a new video has been uploaded. Okay, I'm making shorter videos than I used to, and I think these are going down positively with the students who watch them. So Section B. Answer all questions in a space is provided. Okay. Question 11. Helium gas can be used to fill balloons, and a cylinder of helium gas contains 1.20 times 10 to the 24 molecules. So that will be N in our equations. The equations are back at your formula sheet, so you need to know which equations to use. And it says the temperature of the gas is 293 Kelvin. So we know the temperature, we know N. All right, so they want you to calculate the internal energy. Now, in A level, they don't tend to give internal energy the correct letter, I've noticed. So what the correct letter, as far as I'm concerned, is U. All right, so here I've put U as the internal energy. Now, internal energy is basically related to kinetic energy of the particles, and as well as potential energy, because obviously particles or atoms or molecules, they also have potential energy between them. However, helium gas is kind of an inert gas, so it doesn't really have much attraction with other helium atoms, so that's monatomic. So it is okay to assume that all the kinetic energy, the internal energy, is due to kinetic energy. And this equation, half root mean squared speed squared, or mean square speed, I should say, times the half mass is equal to kinetic energy. This equation is given to you, So maybe I should have put it all in, maybe I should have put it all into a box. So this equation is on the formula sheet. So the mean kinetic energy of the gas is equal to 3/2 K times T. KT, like a girl's name. So the mean kinetic energy is per molecule, obviously. So it's the average molecule's kinetic energy, half mc squared. Okay. Now this is a statistical value, and you need to know how you get it. So you need to go and revise that if you don't. And since the gas contains n molecules, then the total internal energy will be n times what we put above, which is 3/2 kT. Now, since we know the temperature, we haven't been given the value for c squared. We don't know c squared, but we do know the other side of the equation. So we know that the left-hand side of this equation is equal to the average kinetic energy, so 3/2 kT. And since we have n molecules in the question, and each one has the mean kinetic energy, you just need to multiply 3/2 kT by 1.2 times 10 to the 24. So you multiply that, and the constant, K, Boltzmann's constant, is given to you in the data sheet at the back, which is 1.38 times 10 to the minus 23, and you multiply that by temperature in Kelvin, and the answer to 3 significant figures is 7,280, and if you round it up to 2 significant figures, you will get 7,300. I think either 3 or 2 should be marked correct. So that's a 2-mark question, and as I was telling you in the multiple choice section, I think this unit is quite mathematical, so you have to do quite a lot of maths to earn your marks. So it's good for those people who are good at maths. Question 12 is about specific capacity and changes of state. So it says bronze is a mixture of tin and copper. tin melts at a much lower temperature than copper, and they've got 2.7 kilograms of solid tin at a temperature of 295 Kelvin. So the starting temperature for tin is 295 Kelvin. It's added to 10.5 kilograms of molten copper. So the copper is already melted. So you're basically adding solid tin to molten copper, and that will make an alloy. Okay. At the temperature of the molten copper that you put the tin in is at 1520. Yeah? So if the copper is already molten and tin melts at a lower temperature, that means the tin will melt when you put it in. So it tells you the tin melts and mixes with the copper to form bronze, molten bronze. Okay? So they want you to calculate the final temperature of the mixture. So the final temperature, I'm calling it theta. So I'm going to find theta for you. Now what you've got to do mathematically is use simultaneous equations. So we need to use this equation for specific capacity. I've used delta T, and I think in the formula sheet they use delta theta. And the equation for latent heat, okay? Well, because it's got to change state as it's solid, and it's got to melt to become molten tin. All right, and then they're giving you some data here, yeah? So we know the masses were given to us, yeah? So I put the masses here. So we know the two masses, and we know the specific capacity of copper. So the copper is going to lose heat. That wasn't very good. The copper is going to lose heat. So the first line is copper. And then the second bit of information is the heat capacity of solid and molten tin. And they're telling you it's the same value. I'll be very surprised to find, and I haven't looked into it, that they will be exactly the same. Okay, because for example, the specific capacity of water is not the same as the specific capacity of ice. So it'll be interesting for you to go and do some research on that out of interest. And then they've given you the other thing you need, which is a specific latent heat of fusion for tin. And that's when you need to put that in this equation. Okay? Because as well as changing temperature, it's also changing state. So you've got to think of both. So as concepts, I've put the first concept, concept 1, is that the internal energy from molten copper, so basically the heat capacity stored inside the molten copper, yeah, is going to heat 2.7 kilograms of tin and melt it. So we need to use the heat capacity equation and the latent heat equation. Right. Concept 2 is then after it's melted, the mixture, bronze, will increase in temperature, yeah, to a final temperature above the melting point of tin. Okay. So at the bottom, I put down what's really happening. So the tin starts at 295. It then heats for a while. It then changes state, and then it carries on heating to the final mixture when thermal equilibrium has been reached. The final temperature will be theta. Now we don't know, this is just a sketch, and obviously the further you go to the right, the more time and energy you put in, and that correlates to a greater temperature increase. While it's changing state, as you know, it does not change temperature. So here is the melting point, and we don't know what the melting point is. All right, so concept 1 we're looking at, so the energy transferred from copper, to heat the tin to the melting point, yeah, will be MC delta T, yeah. So that's where C is for copper. So we've been given the heat capacity of copper as 572 in the data above, and we know the mass of copper, so 10.5 kilograms of copper with this heat capacity of 572 will go down from 1520, yeah, minus theta, yeah, the final temperature. So change in temperature will be initial minus final, and it will give you a value of, actually, I think I got this wrong, and I think I've got the answer slightly wrong at the bottom. Surely that should be final temperature, so I've got these wrong. Now I understand why I disagreed with the mark scheme. So it should be the other way around. It should be theta minus that, I think, because the final temperature is that. Let me have a look at the mark scheme for you, see if my mind is working properly. It doesn't actually make much difference in the final answer. It's a small difference. So energy is transferred from the hot copper, the molten copper, to heat the tin to the melting point and then heat it further, okay? And at that point, the temperature is going to drop. So it doesn't really matter. The amount of energy is going to be the same, yeah? I'm just wondering whether it should be the other way around. Anyway, so the energy transferred to the tin is then equal to MC for tin. This is the MC, the C for tin, times the temperature change for the tin, yeah, which is going to end up at the thermal equilibrium temperature of theta, plus the change of state energy, the mass times the latent heat value, which is given to us in the data above as 5.92. So this is the ml part, yeah, that has to be added. And this time I put the final temperature minus the initial temperature. And I think in the for the copper, I should have put theta minus 1520. I'll have a look at the mark scheme afterwards and see what they've done. So this is the, if you like, this is the energy 1 must be equal to the energy 2, because this is the energy being lost by copper, and it should be equal to the energy being gained by tin. They should be the same. So that doesn't go anywhere else unless we lose it to the surroundings, but we're assuming we don't do that. So energy 2, when you simplify it, comes out to this, yeah? Plus the latent heat, which comes to 1.60, okay? So if these two energies must be equal, yeah, then you equate the final answer here with the final answer here, and then you put the thetas together and you solve for that. So I think I might have been 1 or 2 degrees out, because I think it only makes a very small difference if I've made a mistake in this section here. So that's what you got to check, that I got it wrong, okay? The bit in red. Should it be theta minus 1520? And we'll have a look at the mark scheme next. All right, so when you do that, you'll find that I've worked it out to be 1387, yeah? So I put all the thetas together on the left-hand side. I put all the thetas together on the left-hand side, and that should give you this answer, okay? And I gave to 1387 to 4 significant figures. I then round it up to 1390 to 3 significant figures. So I might lose a mark, okay? It says error on the mark scheme, but it could be my error in misreading the mark scheme. So let's see if I can show you question 12. All right, so see their answer, they haven't explained it as fully as mine. This is their answer. So let's see, which bit are we looking at? In question 12, we're looking for the energy transferred to tin. See, they've done it here as well. 1520 minus theta. I'm just wondering whether that should be theta minus 1520. So they've done the same, and maybe that's why I made a mistake, because I didn't put final minus initial. Okay, now will that make a big difference? You'll see they've come up with 1386, and I think I came up with 13 whatever I did. If you can have a look, you'll see. Okay, so they've done that. They haven't explained the steps as clearly as I have, so I hope that you find that useful. Okay, And I noticed something else that I felt that they'd done wrong. I'll let you go through it and see, because I did this a couple of days ago, and I can't remember what I noticed. Yeah? Energy transferred to copper must equal, so this is correct. Yeah, energy 1, I said energy 1 must equal energy 2. Yeah, so the energy lost by the copper must be equal to the energy gained by the tin. Yeah. I don't know, something I did notice, there was a minus sign in the wrong place. Anyway, without having to go through it again from scratch, it will take me too long to explain in this video. Anyway, there may be an error, slight error, but actually it doesn't make much difference to the final answer. So I might be losing a mark, the examiner might be losing a mark. So they're basically giving you a mark for use of MC theta. So if you've done that once correctly, correct use of ML, and equating the two energies, but obviously it has to have the numbers in it, and rounding up to theta, the final temperature, to 1390 Kelvin. As I said, these Unit 5 papers have a lot of maths where you can make slip-ups in the minus sign and things like that. Okay. Now I do remember when I went through it, because obviously when I did it, I went through it much more carefully than when I'm trying to explain it now to you. And with all these numbers on the page, it's difficult to decipher. So I'll let you see if you can find it, and if you do, put a comment in under the video, and one day I'll have a look at it when I get a bit more time. So if you found that useful, thank you for watching. Give it a like, share it with your friends, and subscribe so you know you'll be notified when the next video is uploaded. I think that's long enough for a video. Thanks for watching. Catch you next video. Bye for now.